Hello, my name is Ege Karaibrahimoğlu and I'm a first year student at Bilkent University. I am currently studying in the electrical engineering, and this project is part of my Physics 101 coursework. In this project, I will explore the concept of the center of mass, a fundamental topic in physics that plays a crucial role in understanding balance and stability. For this experiment, I will use several tools and materials, including a cylindrical pivot with a radius of 1 cm to balance the shapes. The geometric shapes used are an equilateral triangle with a base of 9.24 cm, a height of 8 cm, a thickness of 3 cm, and a mass of 55 grams. A circle with radius of 3.5 cm, a thickness of 1 cm, and a mass of 35 grams. And a square with a side length of 5.5 centimeters, a thickness of 3 centimeters, and a mass of 50 grams. Additional tools include a scale to measure the masses of the shapes and a ruler to determine the dimensions accurately. The goal of this experiment is to measure and compare the theoretical and experimental center of mass for these shapes, both individually and in pairs. By doing so, I aim to understand how mass distribution and alignment affect the center of mass in composite systems. Now that I have explained the setup and materials, let's begin by measuring the center of mass for each shape individually. Okay, now we are going to check is theoretical center of mass is true or not. The dots that I showed is the theoretical center of mass. Now I'm going to figure out by using pivot point this stick. Now circle. Now I'm going to put the rectangle. And the last I'm going to use triangle. As you see, theoretical center of mass is correct. Now let's go to the next step. After determining the center of mass for each shape individually, I analyzed composite systems combining the equilateral triangle with the circle, the equilateral triangle with the square, and the circle with the square. Each pair was positioned tangentially at the origin. The theoretical center of mass was calculated based on the shapes, geometric properties, and ideal alignment. However, during the experiment, the shapes were placed on a 1 cm radius pivot, which introduced slight shifts due to the difficulty of precise placement and the large pivot size. These factors caused small deviations between the theoretical and experimental results, demonstrating the impact of real-world conditions. Despite this, the experimental values closely aligned with the theoretical predictions. Through this experiment, I learned how the center of mass is influenced by the distribution and alignment of shapes in both theoretical and real-world setups. I also realized the challenges of achieving precise placement in experimental conditions, such as balancing shapes on a 1 cm pivot. Despite these challenges, the results demonstrated that theoretical models are reliable tools for predicting physical behaviors, while practical limitations highlight the importance of careful measurement and setup.